there, Wind Power students. Dr. Shragi here, and I am giving you a lecture now about part of the second chapter of the Landberg textbook about atmospheric variables and the forces acting on the atmosphere. It is another really stormy day here in Indiana. There's a pouring rain out the window right over here, and so you may hear some really interesting claps of lightning, thunder, or see some flashes of lightning. It's kind of exciting out there. Anyway, to understand what we're going to be talking here about these forces and so on. Now, this part of your textbook, by the way, is only a couple paragraphs long, but I think the author didn't do you a great service here, because in order to understand wind and the processes that are creating wind, and to understand how wind gets its energy and so on, we're going to need to know this in more detail than what the author did. And first we need to really understand what air is like. It's easy to not really have a good handle on what the behavior of atmosphere is like and how gases work and so on. Here we have a kind of a fairly standard looking animation going as to what air is like, where it's sort of this mixture of different molecules. In the case of our atmosphere, it's mostly nitrogen with some oxygen, roughly 3/4 nitrogen and 1/4 oxygen, with a few other trace gases all on there. And all those air molecules are moving along at high speed in the air. The average speed of those air molecules is about 1,000 miles per hour, 1,100 miles per hour is what I have here on the slide, which is about 500 meters per second. And these little molecules are colliding a lot. I mean, the mean free path, the average distance an air molecule can go before it collides with another air molecule, at least at the density at the surface of near the surface of the Earth, is only 9.22 times 10 to the negative 8th meters. So in other words, move that decimal place 8 digits over to the left. I mean, this is a very, very, very tiny, tiny number. That if you work out that high speed that those molecules are moving and the small average distance they can go before they collide with another molecule, you figure out that there's over 5 trillion, is that right? Trillion? Yeah, 5 trillion collisions per second for any average molecule. So the molecules are just moving really, really fast, but not getting very far. They just collide with the gas molecules all around them. And once you have this vision of how the air is almost just bubbling with energy, and just such an enormous amounts of energy, and all the kinetic energy, these little molecules bumping around, suddenly the variables that we use to describe what's going on in the atmosphere start making a lot of sense. So we're going to talk, as does your textbook, about pressure, temperature, density, and so on now that we kind of have this vision of what air is really like. I mean, even a sample of air that seems like it's not doing much is just alive with energy. And so let's start with pressure. Now, the classic thing that we do in an intro to meteorology type course, for example, would be to tell you that there's 2 ways to think about pressure, and how these 2 ways of pressure can help you understand different things about the atmosphere. The first thing that we talk about when we say pressure is that one way to think about pressure is that it's the force of all these little air molecules colliding with a unit area. So like if you had a 1 meter square area, as these molecules are hitting that little area, how much force are they exerting? Okay, that's one way to think about pressure, and it helps us understand things like the units of pressure. I mean, it's the force. Well, the metric unit of force is the Newton, and as those molecules hit a square unit area, or the square meter, so the units of pressure should be newtons per square meter. As it happens in the metric system, there is a term that we use for a Newton per square meter that's called a Pascal. You may not be familiar with that term, but a Pascal is a unit of pressure. It's abbreviated PA, and as it happens, Pascals are really, really small. The pressure at the Earth's surface is about 100,000, it's 101,325 Pascals on average. That is a big number. Meteorologists don't want to be writing these giant numbers on their weather maps. That's not a helpful thing. So generally, meteorologists want to work with what are called hectopascals, HPA, which is like Pascals divided by 100. The word hectopascal doesn't roll off your tongue. As it happens, it's related to the unit millibar. And so hectopascals and millibars are effectively the same thing. Millibars, or MB, will be the unit that we tend to talk about pressure in, although most of the time when we're working with equations, we are going to need to use the actual SI metric unit of pressure, which is Pascals. Just to give you a sense, though, the average sea level pressure then at the surface of the Earth is about 1,013 millibars. I'm not sure why there's a stray S there in the front of that. It's 1,013 millibars on average. So like if you just use your favorite weather website, and I hope by now you have your favorite weather website, and bring up a map of, say, sea level pressure right now. Here's a map of the pressure of the Earth all over the United States at this particular time or whatever. And, oh, if you actually look at the key there, you can see that there's areas of high pressure off, say, like in Canada, in Manitoba and Saskatchewan and so on, where the pressure is something like 1,022, 1,024 millibars. And there's areas of low pressure in, say, California and Arizona. That's actually a heat low for students who know more about meteorology, where the pressure is a little bit lower, more like 1,008 millibars, 1,006, something like that. Just to give you a sense, though, we have these weather patterns that are described by areas of higher or lower pressure, but we'll be learning so much more about that in the coming days. Another way to think about pressure, we always say that there's two ways to think about pressure. Another way to think about pressure is just the weight of the air above you. So, air has mass, Earth has gravity. Anytime you have mass in the presence of gravity, you have weight. And so, all those air molecules up above you, they all have weight and they're all pushing down. And that's another way to think about pressure. And you can think of this column of air that extends from the surface all the way up to space. And that is the weight of all that air pushing down on that area at the bottom. The most useful thing about that understanding of pressure is that it makes it very clear that pressure is always decreasing with respect to height. That first explanation of how it's the force of all these little molecules hitting a surface doesn't really explain the fact that we know pressure always decreases with respect to height when we take measurements. Well, if you know that pressure is the weight of the air above you, that makes good sense because, as you go up, there can only be less air above you than there was when you were down lower, because now as you go up, now some of the air is below you. So pressure can only decrease with respect to height, and you can see in any meteorology textbook a kind of diagram like this, where it shows height on the y-axis and pressure on the x-axis. You can see how pressure decreases as you go up in the Earth's atmosphere, all of which is described well by various equations and so on that are not the direction in which we're going with this. All right. Pressure. Another one, temperature. Another state variable, to use the right term, that describes how the atmosphere is behaving. Now, it's a very common thing that even grade school kids in their science classes learn, is that temperature is about how fast molecules are moving. And that's not a bad picture to have in your mind. On the other hand, it's probably more correct to say that the temperature is proportional to the mean kinetic energy of the molecules. Let's be clear about that. If you have a sample of air, it's going to be made up of a mixture of gases. And all of those gases that are in there all have the same temperature. Okay? They have the same temperature. It isn't like there are hot gases and there are cooler gases and some of the molecules are hotter and some are cooler. It doesn't work that way. Sometimes people think that that's how global warming works. We're putting hot gases in the atmosphere. No. All the gases have the same temperature once they're mixed together. But that doesn't mean they all have the same kinetic energy, but they have the same average kinetic energy. See, here's the deal. Let's think back to our definition of kinetic energy. We're in the kinetic energy. Well, one way to think about it, kinetic energy of any object is 1/2 mv squared, where v is the velocity and m is the mass. So if all these different kinds of molecules that are mixed together, oxygen and carbon dioxide and nitrogen and everything, all have the same temperature, they all have to have the same kinetic energy. But they all have different masses. So since some of the molecules are heavier and some of the molecules are lighter, well, to have the same kinetic energy, the heavy molecules don't have to be moving as fast. A heavy molecule moving fairly slowly has the same kinetic energy as a light molecule moving really fast. So if you have a mixture of gases, don't get the idea that they're all moving the same speed. They in fact move at wildly different speeds. Here I've listed 4 gases: nitrogen, oxygen, nitrogen, helium, and hydrogen. And for each of those gases, I've given you the molecular weight. I won't read you the numbers here, but you can see how oxygen is by far the heaviest of these O2 is by far the heaviest of these gases, with hydrogen being by far the lightest. And in fact, you can figure out, it's actually a problem they do in the ATS 114 lab to figure out what is the speed of these molecules. And you can see that oxygen molecules have a mean speed of about 1,070 miles per hour at the density and the temperatures at the Earth's surface. Nitrogen molecules, though, are lighter, so at that same temperature and density, they have to be moving faster, 1,100 miles per hour. Helium molecules, on the other hand, are very light, and they move at over 3,000 miles per hour at the same temperature. And at the same temperature, hydrogen moves at over 4,000 miles per hour. So these lighter molecules are moving a whole lot faster. In fact, that's a really high speed those molecules are moving at. In fact, those lower two ones, the hydrogen and the helium, those light molecules, that speed there, the listed though, that's actually greater than the escape velocity of the Earth's gravitational field. That's why we don't have a lot of helium and hydrogen in the Earth's atmosphere. In fact, we have basically none. All hydrogen and helium molecules that are in the Earth's atmosphere are on their way out. They're in the process of working their way up, and eventually they'll get themselves high enough in the atmosphere, the molecules are farther enough apart that they won't. Their mean free path is infinite. They're not going to hit another air molecule, and they'll just head off into interplanetary space. Alright, so temperature. I get it. It's about kinetic energy of gases. I understand this molecule idea now. Some are moving faster, some are moving slower. I get it. In our equations in general, we're going to need to be using the units of Kelvin as our way of expressing temperature. Sometimes we'll need degrees Celsius. If so, you can convert back and forth between Celsius and Kelvin using the basic idea that Kelvin is just 273.15 greater than the temperature in Celsius. That way, Kelvin is always a positive number and so on. Okay, density. Density is another state variable that describes what the gases are doing. We've already talked about quite a bit about density in this semester, so I'm not going to get too bogged down about it. We'll remember that our symbol for density is rho. That one that kind of looks like a letter, like when it's typeset anyway, it kind of looks like a lowercase p. We already talked about the fact that the units of density are kilograms per cubic meter, where, you know, in a cubic meter, how many kilograms of the gas or whatever are in there. And just like pressure, density always decreases with respect to height. And perhaps more importantly for the applications we're going to be seeing, there's a way in which the three state variables we've learned so far, pressure, temperature, and density, are related. The equation that describes those three state variables and how they're related is the so-called ideal gas law, which I wrote to you there in the form P equals rho RT. If you're a survivor of like high school chemistry or high school physics class, you may have seen it in other forms. Okay, there's other ways to rearrange the variables or make substitutions. PV equals nRT is what you learn in chemistry. That's one of the little things I remember from like high school chemistry class. It doesn't matter. The form that works best for atmospheric applications is P equals rho RT, where this R is the gas constant. I will give you the gas constant when we get to a point in the course where we need it to solve some kinds of problems. But anyway, so like if you know pressure and temperature, you can solve for density, or if you know density and temperature, you can solve for pressure using the ideal gas law. Velocity. Here when we're talking about velocity, we mean like as in the speed of the wind, not the speed of the individual molecules. The individual molecules, remember, are zipping along at like 1,100 miles per hour, but obviously the wind isn't moving that. Wind is the bulk movement of all the molecules. I mean, each individual molecule is bumping around like crazy, but how is the group of molecules moving? The analogy I like to draw is to kind of think about a school bus. Okay, here's a school bus. Can you picture it full of kids that are acting crazy and they're running around and they're bumping into each other and so on? But the whole bus can be moving along too, right? The fact that any individual kid might be running towards the back of the bus or toward the front of the bus is not relevant compared to the whole group of kids in the bus all moving in one direction. In the same way, the group of air molecules is headed some direction. Individual air molecules within there are bouncing around at 1,100 miles per hour or over 500 meters per second, but the group of molecules is what we mean by winds. Winds, of course, are in general much slower than the movement of the individual air molecules yourself. It is not a coincidence that you've never heard of an 1,100 mile per hour wind. In fact, it can be shown in a much more complicated class than this that you can't get winds that high. The gas molecules no longer behave as an ideal gas and so on. You guys got to this point in your education by having had lots of math classes, lots of stats, lots of physics classes, lots of science classes, whether they were in high school or preparatory classes in college and so on. And one of the things you've undoubtedly seen in your education is vectors, you know, where you represent a property as an arrow that has both direction and magnitude. Velocity is a vector. It has wind speed and wind direction associated with it. And that is one way in which meteorologists often describe the wind, is to describe it in terms of the direction it's coming from and the speed. Remember, we always describe winds in terms of where they're coming from. North winds are from the north. A sea breeze is from the sea. well, we could describe the wind as from the west at 10 miles per hour or something like that. A more sophisticated way to describe the wind is to describe it in terms of its components, to describe it in terms of how much of the wind is coming from the east-west direction and how much is going in the north-south direction. To understand that, we need to talk about the coordinate system that we'll be using in this class. I've got Nebraska kind of here as in perspective, just to sort of help you so you can see what's going on. X is in our coordinate system always in the direction of from the west to the east. In a three-dimensional coordinate system, our Y will always be pointing from the south to the north. And in a three-dimensional coordinate system, our Z will always be our vertical coordinate, going from low to high. Okay, there are lots of coordinate systems. Meteorology is full of learning about lots of different kind of coordinate systems. The good news is, in the context of wind power, these are going to be all we need. All right, so when we have a coordinate system like this that just sort of works in 3 dimensions like that, we can describe the wind then in terms of U, how much of the, the component of the wind in the west to east direction, plus V, the component of the wind in the south to north direction, plus W, the component of the wind in the, the vertical direction. So at any given time, the wind is some kind of 3-dimensional wind, and we can describe it as how much of that is in the west-east direction, how much of that is in the south-north direction, and how much of that is in the vertical direction. And you'll see lots of examples of this. If this brief overview of how we describe the winds isn't helping, don't worry, we're going to be able to put that into some good context soon. Now, in the case of wind power, we hardly ever need to worry about the vertical component of the wind. So most of the time, you're not going to need to worry about the direction of the vertical component of the wind. You can just talk about horizontal winds. And frankly, most of the time in wind power, we're not terribly worried about the direction of the wind because the wind turbine will just turn to face upwind. We just are worried about the speed of the wind coming through it. And of course, just to be clear, our SI System International metric system unit for velocity is meters per second. We're not going to in general solve equations in miles per hour or something like that. One more atmospheric state variable they want you to know about is humidity. Now, let me tell you, if you're a survivor of ATS 113 or some other atmospheric science class, you've already seen that there are actually lots and lots and lots of ways to describe the amount of water vapor in the atmosphere. It's actually a very complicated problem to come up with an ideal way to describe the amount of water vapor in the atmosphere. As it happens, that's not going to be a huge factor in what we're doing here. There's obviously a lot of meteorological significance to the amount of water vapor that's in the atmosphere in terms of forming clouds, making precipitation, and so on. But as it happens, that is not going to have a huge impact on wind power. It isn't like, it'll be windier when it's not humid and it's going to be less windy when it's more humid or something like that. But at least there are a handful of places in the text where we're going to run across where we need to know the symbol for understanding what we mean when we're talking about humidity. And I'm not entirely thrilled by the fact that the textbook has decided to use the symbol Q for the humidity, where this is specifically the type of humidity called water vapor mixing ratio. Here's why I'm not happy about this symbol here. Water vapor mixing ratio is a real thing in atmospheric sciences, and Q is very much not the symbol for it. And Q actually is the symbol for a different way of describing the amount of humidity in the atmosphere, but this is not atmospheric thermodynamics. This is not this is not cloud physics, all of which are 500 level atmospheric science courses. In this context, we're going to use the symbol this book likes, which is Q, which is the water vapor mixing ratio, which is just a ratio of how many, in a given sample of air, how many kilograms of water vapor are in that air, divided by the number of kilograms of dry air that are in that sample. So it's just a ratio of it's like a recipe. To make this air, how many kilograms of dry air molecules, things like nitrogen and oxygen and carbon dioxide and so on, are in there, and how many kilograms of water vapor molecules are in there. Now, as it happens, water vapor mixing ratio is a very, very tiny number. And it's unitless, and it's tiny. Scientists hate unitless. Scientists don't like tiny numbers. So in general, when you see them describing the humidity, they usually have multiplied the mixing ratio by 1,000, which changes its units to like grams of water vapor per kilogram of dry air. And well, that works better because you get numbers that are like 2.5. Okay, so that means that there would be like 2.5 grams of water vapor for every 1 kilogram of dry air molecules in that sample. Okay, well, it's just the terminology. Again, there's not a lot of wind power applications to that. We'll see that a couple times over the course of the semester. Now, before we start attacking the whole business of forces in the atmosphere, I want to ask you a couple quick questions. Question 1. What are the SI units of density? Newtons per square meter, it's unitless, kilograms, kilograms per cubic meter, or kilogram meter per second squared. What are the right units for density? Make a choice from those 5 options and get a little feedback before you move on to question 2.